Okay, I just overrode something. Oh well. Okay, we're ready to start. Exponential laws. Somebody gonna hit the little button back there, please?
What?
Forget it, I'll do it. Somebody might have to get up.
We know what you were talking about.
Well, let me think. The computer's up there and the video camera's right here. I had my back turned to y'all and I said, somebody hit my button. Yeah, it must be on the wall.
Well, there's all kind of buttons.
There's one button.
Well, now that we have it clear, we know what button we need to mash.
I'll forget it. All right, the exponential laws are as follows. The first one is called the product rule. The product rule is used when the bases are the same and you are multiplying. What do you do to the exponents if the bases are the same and you are multiplying the terms? What do you do to the exponents? You add them. And that is the product rule. Product means multiplying. So when you're multiplying two terms and you have the same base. Now that's the kicker. If you have x squared plus y times y squared, you can't do anything with that. That's like mixing apples and oranges and getting apples. You can't do that. But if they're the same base, you can. The opposite of the product rule is the quotient rule. Quotient rule says that if you have two terms with the same base and you're dividing, what can you do with the exponents? Subtracting, Hubert. That's right, class. Remember, they have to be the same base. So we'll take the red marker. The next rule is called the power rule. The power rule says that if you raise an exponent to another exponent, what can you do to the exponents? Multiply them. Now the first three exponential rules are basically on the mechanics of the mathematics. In other words, how you add terms, how you multiply terms, how you divide terms, and what do you do with terms that are multiplied by themselves 2 or 3 times. So each one of those has to do with an operation of mathematics. This is multiplication. This is what? Division. And this is exponential multiplication, I guess you'd call it. Exponential multiplication. What about adding and subtracting? Well, if you have the same base, you have to have the same exponent, just like a label. Let me back up one, or let me go to another page and address that. The only one left is adding and subtracting. Well, really, there is no adding and subtracting with like terms. It's basically called what? Combining. Because if you have 3x squared minus 4x squared, these right here are nothing but a label. 3 boxes of cereal minus 4 boxes of cereal is -1 box of cereal. In other words, the label doesn't change when you have exponents and you're adding and subtracting. If they're the same, they combine. 4y to the third plus 6y to the third. This is 4 cans of OIL plus 6 cans of OIL is equal to 10 cans of OIL. See, the label does not change. So if you're adding and subtracting terms with exponents, the term and the exponent has to be identical, or the base of the exponent. The number out front doesn't matter. So what has to be the same on these? -1 x squared. Take our red marker. The labels have to what? Match. If they don't match, you can't add or subtract them. And one more thing, they don't change when you take them over to the other side. The label. $3 minus $4 equals -$1. So just taking a side note there, because on this one we covered multiplication and division, but we didn't cover addition and subtraction, and that's why I reviewed over that back there. Now the next two rules, or the next three rules, is basically how to rewrite the next exponent. And I'll call it number 4. Number 4 is called the inverse rule. Now you don't necessarily need the inverse rule to be able to do exponential mathematics. In other words, the only reason we have the inverse rule is because we don't like the negative what? Exponent. Okay? And you might want to put out here negative exponent, and then put we don't like negative exponents. Now it's a cultural thing, because I know some instructors from Asia, they don't care if it's a negative exponent or not. So it's not, you have to do it. But most teachers like to not see a negative exponent. Now, also make another note. Negative exponent is okay in scientific notation. All right? And you need to make that note, because some of y'all are going to say, well, that's a negative exponent. Well, scientific notation is not, it's an exponent, it's a negative exponent, but it doesn't mean the same thing as it does in exponentials. All right? In scientific notation, a negative exponent, negative means left. In a regular exponent, it means it can be switched to the bottom. So it's not exactly the same thing. So that's why a negative exponent is okay or permitted in scientific notation. And in a regular, let me give you an example. X to the -2. That, don't want that. So you use the inverse rule, and I'm fixing to show you. This 2 times 2.0 times 10 to the -3rd, this is permitted, because it doesn't mean the same thing as this. Because this is a number to a negative exponent, this is a variable to a negative exponent. So it's two different animals. Now the inverse rule basically says, if you have a negative exponent in the denominator, flip it, and it becomes what? Positive. If you have a negative exponent in the numerator, flip it, and it becomes what? Positive. Now, did I say the variable out front, or did I say the coefficient out front, or did I say the exponent? The exponent. Some of y'all, if that's a -2x to the n, y'all will try to bring it down and make it positive 1 over positive 2x to the n. No, I didn't say anything about the number in front of the variable. I said This guy right here. The negative what? Negative exponent. So you need to take your highlighter out, and you need to highlight this guy and this guy. Because it doesn't change what's in front of, because there's a negative right here, there's still a negative right here. You can't do that.
You say if there's a negative in the denominator, you move it to the numerator,
It's still a negative. Look, if I give you, if I just say number 1, and number 1 says 1 over negative 2x to the negative 3rd power. Okay, that's the problem I give you. And I tell you to correct the negative exponent. So what would I do? I flip it, right? And that would be negative 2x to the 3rd over 1, which is what? Negative 2x to the 3rd. What did not change? The negative 2. See it? The negative, you can't change a negative variable just by flipping. If that was true, nobody would have an overdrawn balance of the paper. Just flip it. Be nice, yeah. I'd have to do that all the time. Yeah, just flip it. So that is the inverse rule. Inverse rule basically addresses what? Negative exponent. So is it detrimental for you to be able to do this rule? No. It's just nice to have so you don't have negative exponents in your answer. The 5th one is called the inverse power rule. This is a tool, again, aesthetically, meaning looks, or your preference of what you really want to work with. And it addresses a negative exponent on the outside of the parentheses. X to the n over x to the m raised to the negative w power. Now what is causing you to have convulsions on this problem? The negative w. So if you wanted to fix it and make it positive, you just flip what's on the inside. Now, notice I said flip what's on the inside. Inside of what? Okay, this one has parentheses. Does this one have parentheses? No. Different animals. This is a cat. This is a tiger. Okay, they both have 4 paws. They both have a tail, but they're different. All right. This is raised to the negative w. So if I flip what's on the inside of the parentheses, then that will flip this to a positive w. But it won't do anything to these because they're inside parentheses. Now if this was just like that, then it would be x to the negative m over x to the negative n. But since it's in parentheses, and this is out here, this is what happens. X to the m over x to the n raised to the w power. Again, is for aesthetics. This is how I would use the inverse power rule if you had this. Now, somebody tell me why I would use the inverse power rule here. No? Because what's inside the parentheses don't change. Why would I want to make the 4 negative? To make what? The answer come out to be what? Positive exponent. That's fine. That's how you use the inverse power rule. You don't necessarily have to use the inverse power rule. It's just something nice to use. So I would flip it, and it would be x to the negative 3 over x to the negative 2 raised to the what? negative fourth power. And what's, now use the power rule, what's negative 4 times negative 3? X to the 12th. And what's negative 4 times negative 2? Y to, I'm sorry, one of them is Y. Okay, this is Y. Sorry. Y to the 12th, and the bottom one is X to the 8th. And therefore you don't have to worry about negative exponents. So that's an example of why you would use the inverse power rule. You don't necessarily have to use it. It's just something that makes life easier. If these were both positive, would you change this to a negative? No, that would be extra what? Work, because then you'd have negative exponents, and then you would have to flip them after you distribute. This is just like the distributive law. I mean, the power rule that I just used here. After you distribute that forward, do you have it outside the parentheses anymore? No. So once you distribute that forward, depending on where you distribute it, you could distribute it here and get negative 8 over negative 12, and then this is gone. The parentheses are gone, and this is gone. And then you could flip it and make it positive. So once you use the power rule, go back to the power rule and put out to the side works kind of like distributive law. Oops, that's the wrong one. The power rule. Let me work this and do this. It's probably not exactly good, but anyway. Photoshop, copy. That's where it belongs. One. There, power rule. Appreciate it. There. It's kind of like distributive law. Once you distribute that M right here, what happens to the parentheses? They're gone. Okay? Now, scientific notation. Now, the reason I went over this is because some of these two rules right here we're going to use with scientific notation. And this rule you're going to use with scientific notation. So three of the, well, that's not really the rule, that's more of an operation. In other words, if I have 2.0 times 10 to the fourth plus 3.0 times 10 to the fourth, what's my answer? This is a label. When you add or subtract scientific notations, they have to be what? They have to be the same right here. Have to be the same. If they're not the same, then you can't do it this easy. You have to go through and convert them and all that stuff. A lot of people don't realize that. They go through high school and they get to college and they find that out for the first time. Okay? All right, so that's why this is used here. In other words, they have to be the same for you to add or subtract them. These have to be the same right here for you to add or subtract. If not, then you have to do something different. All right. What is scientific notation? Well, you got to know the definition before you can learn how to do it. Now let me go ahead and warn you. There are some people that think they know everything there is to know about scientific notation. And most of the time, 90% of you do. But when I start getting you to add or subtract scientific notations, or multiply or divide scientific notations, that's when y'all go haywire. All right? That's when some of you don't know what to do. So, I do realize that there's other ways to teach scientific notation. I realize that you learned other ways to do scientific notation. I realize that your teacher told you that if it's a large number, you go to the right. I don't do it that way. Okay? And the reason I don't do it that way is because when you get to a multiplying or subtracting or a word problem or addition or division, then you do that big number to the right thing, it ain't going to help you. So there's no use in learning. So what I tell students is, first you got to learn the definition. Usually with very large numbers or very small numbers, placing the decimal to the right of the first number greater than or equal to 1. Now I'm very vague with this definition because usually I'll get a student raise their hand and say, well, I don't understand that definition because I don't know which way you're going. I know, we've only read left to right for how many years of our lives? How old are you? How old are you? How many? 18. So for probably, what, 3 years of your life? No, I'm just kidding. 15 years of your life? I don't know, 10 years of your life you've been reading left to what? Left to right. Now we're going to just all of a sudden go right to left. Just read right to left. My salama. How old are you, Mr. Will? 45. Okay. For 40 years of your life, you've been reading left to right. Why start reading from right to left now? But that's what students do. They say, I just don't know which way you're coming from. Okay. Whatever you say. So let me do one. All right, there's a BA number. First thing to do is place the decimal to the right, first number greater than or equal to 1. Sometimes I say greater than 0, sometimes I say greater than 1. Same thing. What number is that? Huh? No, what number? I said, what number is it? I said, what number is greater than or equal to 0? 4. Some of y'all said 4, some of y'all said, how do you get that? We read which way? Left to right. This says, placing the decimal to the right of the first number greater than or equal to 0. We read left to right. Which one is greater than or equal to 0? 4. So the decimal goes right there. Where is the decimal right now on a whole number? The decimal on a whole number is always beside the last what? Digit. So we got to move it. Now this is where I tell you, if you know how to do it, keep your mouth shut because I don't want you to say anything. Okay? Because I don't teach it the way that you learn. I teach it the way that I learn. 1, 2, 3, 4, 5, 6. So 4.2 times 10 to the blank 6. 90% of you will get the 6 correct. The other 10% don't know what that is. Okay? But out of the 90%, about 15 to 20% of the 90% get it wrong because of the what? Not the 6. But what? What goes in front of the 6? No. It's called a what? Negative or positive? What are those called? A sign. Sign, Hubert. Yeah, that's right. Y'all will get the sign mixed up. Not on these, but when we do the problems of the 15 times 10 to the 4th times 3 times 10 to the 5th. That's where you're going to get them wrong. Okay, so just bear with me. How do you establish this sign? Well, you ask yourself mentally. Mentally. Mentally means what? In your head. Which way do I move the decimal to get original form. Okay, and I'm gonna draw an arrow right here. In fact, I'm gonna draw a red arrow right here. And I'm gonna put red under here and right here. Because I'm looking at this decimal. I've already written this. This is on my paper right here. Which way did I move this decimal in my head to get it back the way it was? To the right. Right this way. Positive. Now, how did I learn it that way? None of you learned it that way. You know why? Because that's the way I learned myself. Okay? Now, I don't do any of this patternization that some of these other high school teachers or other math teachers do. Well, if it's a large number, it's going to be positive. If it's a negative number, it's going to be, or a very small number, it's going to be negative. And then when you get to the problems that really count, you can't do them. Because the answer ends up, you got to move it 2 places or 1 place, and you already got an answer. And those people that learn that, they don't know what to do. So I don't teach it that way. So the answer is 4.2 times 10 to the 6th power. And like I said, 90% of you will get this right with no problem. That's not what I'm focusing on. I'll do a small one here in just a minute, and then we'll move to the problems that y'all go haywire on. Okay, so let's do a nerd. All right, do that one. All right, Brown. Where's Brown? Okay, not staring at y'all or anything, just trying to learn some of y'all's names. Carrie. Where's Carrie? Okay. The quiet ones are the hardest ones to remember. The loudest ones are easy to remember. Sorry, I'm not staring at you.
Well, everybody should know your name then, right?
Yeah, everybody knows my name. No, there's still the deadhead that walks out of my class the first day of class going, I don't know who my math teacher is.
That was me.
I wouldn't say that out
I
loud.
do remember that one.
Yeah, and I live in a trailer out on the pad. Dawson.
Here.
You're Mr. Dawson.
I am
Mr. Dee-Doo. Did I say it right? How do you say it? Dito.
Yes,
How about Charles?
that works.
Okay. Just some I'm just going to not even try. Edwards. Edwards? Oh. Okay. Elliot? Which one's Elliot? Okay. And Miss Grubbs is here. Lee Croy. Which one's Lee Croy? Okay. Miss Littman left early. Pardue is here. Queen is here. Rochester is not here. Roebuck? Roebuck? No Roebuck. Satterfield? Where's Satterfield? Okay. Shaw? Where's Shaw? Okay. Okay, Mr. Smith. Where are you? Oh, there you are. Were you here the other day? Yesterday? Which is what? Monday? You were here? Well, I counted you here. I couldn't remember. I didn't remember seeing you. I didn't take roll the other day, so I think I gave everybody a yes. Vernon. Oh, forgot about James. Where are you at, James? Smith. Okay, Smith is not here. Okay, Mr. Vernon. Okay. Whitfield, where are you? Okay. Williford, if he's here. And Wright. Where's Wright? Okay. All right. Got you all here. So the bureaucrats are happy. All right, here we go. So I'm going to move it. 1, 2, 3, 4, 5, 6. Notice I do not say what. What do I not say? I don't say right or left. I don't do that until the very end of the problem, because that is what you're going to get wrong. Because most of y'all can count. Right? Now, take my red marker. Which way did I move that mentally to get back the way it was? To what? I heard a left. All right. So that's your answer. So your final answer is 3.14 times 10 to the negative 6. Now let me go ahead and say it again. I realize that some of y'all don't do it that way. And that's fine. If you get the next couple of problems correct, and you don't have to use the eraser on your sign at all, then you're fine. Okay? So let's do a couple of those problems, because these are the ones that everybody will get right. I don't put these on the test. Okay? The ones that I put on the test are the ones that's going to be on your SATs or your nursing practical application, whatever practicum test that you have to get in the nursing program, or whatever, all these standardized tests you have to take, whether it be Michelin, Bosch, whatever. All right? So let's do one. Let's say we have 3.0 times 10 to the 4th times 6.0 times 10 to the 5th. All right, I'm going to give everybody a couple of minutes to work on it. And if you don't know how to do it, just meditate. Do not use a calculator, because I've not told you to get out a calculator yet, so you shouldn't even have one. Do not do like some, we had some brain children. You know what they did? Changed it to zeros. Changed it to 33,000 times 60,000 or whatever, and then they commenced to doing long multiplication. Yeah, that's smart. Now, some of you are going boom, boom, boom. Some of y'all are going, I don't know how to do it. Don't feel pregnant, because there's a lot of people that don't know how to do these, because they were not taught how to do it. They were just taught, it's a big number, you do this, and it's a small number, you do this. So what is 3 times 6? 18.0. Yep. And the reason I put 18.0 is just to show you what a decimal is. You don't have to put that. And then I'm going to say times 10 to the 4th times 10 to the 5th. Now what is this? Same what? Same base, and what are we doing? So what do you do to the exponent? Add them, Hubert. That's right, class. 4 plus 5 is, are we done? Why not, Ms. Edwards? Just the way I asked it, right?
Yeah, no.
What have we not done?
Put it in scientific notation.
It's not in scientific notation. Why? Because this is besides the second number greater than or equal to 1. You got to put it where? The first number, which is 1. Go ahead and do it. It's just one place. If it's a bigger number, you have to do this. And it's a smaller number, it's a $100. ask yourself that question. Which way do I move it manually to get it back the way it was? So I'm going to do right here, one place, 1.8 times 10 to the 9 blank 1. Take the red marker. Which way did I move this decimal to get back the way it was? What? Get it back the way it was. To the right. I guarantee you somebody in here has 8. And if you have 8, what was that? What did you do? What did you have?
No, I had 10.
Okay, whatever.
Like you did
All right.
that, and I was like, oh, no one's 8.
The answer is 10 to the 10th power. So your answer is 1.8 times 10 to the what? 10th power. That is the only way that I have learned to do that and not get confused. But you do whatever you want. If it ain't broke, don't fix it. If you got 1.8 times 10 to the 10th, and you did it your way, and it ain't broke, you keep doing what you're doing. That, or they may ask you to put it in regular notation, which that would be move the decimal 10 places into a bunch of zeros. But I'll show you that in just a minute. Look what we actually did. Some of you do this right here, and you actually don't know what you've done. What have you done? You've taken what? 30,000, and you multiplied it by what? 600,000, and you did it in your head. And you got this number, which is 18 billion. And you feel good about yourself. I'm missing one. Did I do it 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's right. 18 billion.
You count from zero.
Hmm?
You count from zero because you move to 10. Count from zero to 8.
Yeah. Yeah. 8 is a billion. 6 is what? A million. What would, if 8 is, let's see, 8 or 9, I'm sorry, 9 zeros. 9 zeros is a billion. What about 12 zeros? Trillion. Right now, the United States is $21 trillion in debt.
Yeah, apparently it'll take every American citizen
Like $30,000 a piece.
$54,000.
Oh, that's like,
And we want to have everybody go to community college free next. You know, there's an old saying, nothing is what? Somebody's got to pay for it. I love it when these people at the retail stores go, oh, we will give you this free if you do this. Whatever. Nothing's free. All right, let's try another one. All right, let's see if I can discourage y'all with this one. Let's go with All right. Now, if you are a little bit apprehensive about scientific notation, in other words, you didn't know if you really had a good grasp on it in K through 12, and you really don't know if you have a good grasp on it now, then you need to write down every what? Every step. So what my advice to you, those people right here, you know 45 divided by 3 is what? 15. So you know that. That's not a problem. But this part right here, why is this a problem? Huh? I heard it earlier. That's what I heard. It's what? The negatives. And anytime you have a negative and you're adding negatives, some of y'all did it for me. Okay? I'll go into spontaneous combustion. So what do? You write it step by step. 10 to the negative 5. What? What do you do when you divide exponents? You subtract them. And that would be negative 5 minus a negative 6. And what happens when you have two minuses together? So 15 times 10 to the what? First power. It's not in scientific notation. 1.5 times 10 to the first blank 1. Which way do we move this decimal in our head and get back to the way it was? To the right. So the answer is 1.5 times 10 to the what? Second power. And I guarantee you somebody in here got to the first 0 power. I didn't hear you. If somebody thought it fell off the ladder.
That's it.
Yeah. So you took, let's see, 4, 5. 1, 2, 3, 4, 5. You took 10, 100,000, 10,000, 100,000, millions, 45 millions, and divided it by 10, 100,000, 10,000, 100,000, 3 million. So you took 45 millionths and you divided it by 3 millionths in your head, and you got 15 or 150. You see why I laugh at those people, and I do laugh at you. If you take this and turn it into this and then do long division right here, you see why I'm laughing at you? Because what are you doing? You're doing it the hardest way possible to do it. Or you depend on a calculator, and if you mess up one of these zeros, guess what? The calculator's going to give you the wrong answer. These are your two answers. Sometimes the directions will ask for scientific notation. Sometimes it'll say regular notation. And you feel good about yourself. All right, let's do a homework problem that you're going to see on the test. And if I put a word problem on the test, it's going to be from scientific notation. But I'm trying to discourage you as much as possible. 5.6. Yeah, that's one, but that's not a word problem. That's a good test question. 42 million divided by 6 millionths. That's going to be a BA number. All right, there's one. That's a test question. In June 2010, the population of a large country was about blah, blah, blah people. And the population of the world was about blah, blah, blah people. Determine the ratio of the country's population to the world's population by what? God, they even tell you what to do. Dividing the country's population by the what? World's population. So do that. Write your answer as a decimal number, not in scientific notation. So that means y'all need to start working on it. No meditation on this one. You need to be working. Now in this problem they tell you what to do. So you shouldn't get this one wrong. They tell you to divide the bigger number, the small number by the what? Big number. So I'm going to write 3. $309.5 million. I'm just going to write that out. 309.5 million. And 6.74 what? Billion. So before we get started, I need to, I'm going to rewrite these so I can see what the actual scientific notation is. 309.5 million means 309,500,000 what? Okay, so we're going to write that out. 309,500,000. Okay, and then this one is 6 million or 6 billion what? 74 what? 74 million. Okay, 6 billion, 74 million. Now, I do this, and I've got 2 degrees, and I still do this. So, unless, you're just gifted and you know already what that is, that's fine. But I do this just to make sure. Now, where's the decimal? There's the decimal there, there's the decimal there, so I'm going to move it, and then you can come up with a little pattern for this. Watch. 1, 2, 3, 4, 5, 6, 7, 8, 9. A while ago we said that a billion was what? 9. So you could say 6.74, and then this is times 10 to what? 9. So that's a little trick you can use, or you can do it like this. Okay? Now, what's this one? 1, 2, 3, 4, 5, 6, 7, what? 8. So, this case, you can't say that is 8 because what? You got this, you say 6. This is 6, and then what? 7, 8. You could do that if you wanted to. But this one we could do it because this is already in what? Scientific notation. Yeah, we're supposed to be scientific notation. That's in scientific. It's one decimal to the right. Instead of times 10 to the 9th, we got a word here. Okay? So if this one was written like this, then you could do the 6 with this. But it's not. So this is 3.095 times 10 to the what? 6. I'm sorry, 8. Sorry. All right. So there's that, and there's that. Now we just put it over itself. 3.095 times 10 to the 8 divided by 6.74, and yes, you use your calculators for this unless you're Rain Man, times 10 to the 9th, and that's going to give you blank times 10. What's 8 minus 9?
What?
-1. Somebody take 3.095 and divide by 6.74 and give me 3 digits. Point something. What is it?
0.459.
Is this in scientific notation? No, it's not. So I've got to move it one place. So that's going to give me 4.59 times 10 to the -1, blank 1. Which way did I move this decimal right here in my head to get it back the way it was? To the left. And your answer is 4.59 times 10 to the -2. Well, Hubert, that's not right. Okay, let's hold on. We'll see who's right. It says type as a decimal. So I got to move this how many places? So 0.0459. That's my answer. And it says round to the nearest what? Nearest thousand? 0.04 what? 6, Hubert. That's right. So let's look. Because somebody out there is saying that I didn't get it right because I didn't do it their way. 0.046. Well, if I got it right, then what does that mean about your way? You got it wrong. Now you believe me? Because somebody out there, don't raise your hand, somebody out there got -1 or whatever, I don't know, 0. Somebody out there got 0, but I don't care about who it is. You did it wrong because it's not the answer. All right, y'all get out of here. Have a good day. I'm glad y'all got to see me.